Well, in some of theorem 2.3.27, we've already talked about any column vector is a linear combination of the standard basis, any matrix a linear combination of the standard matrix basis. So now I want to talk about these two guys. I'm actually going to start with this one, and rather than putting an I here, I'm going to put a J. It'll be more natural if I do that. Okay, so let's look at it. A times EJ. Let's look at the ith component of that. What would that be? Well, that would be a sum over K of A, let's see here, A I K E J, the kth component. And let's see here, that would be, A is m by n, so we're looking K equals 1 to n for what it's worth. Okay, now, the nice thing here, of course, is that by definition, this is precisely Kronecker delta JK, and so what we have is just a, well, the summation collapses down. The only thing non-zero in it is when J is equal to K, and so we get Aij. But of course, you may recall that that's exactly the jth column of A and the ith component of that. Okay, but this is true for arbitrary I and j, so therefore we have this wonderful, neat little formula that if we take the product of A times the jth standard standard basis, we just get the jth column of the matrix. Very important little calculational tool we need to use. Now, I suppose you could just take the transpose of this and get that one. I'll actually work it out. So if we have EI transpose times A, all right, and we look at the jth component of that, well, again, by one of the special cases for matrix multiplication I wrote in class, we've got sum over K. This time K equals 1 to m. And we're looking at EI transpose the kth component times a kj in this case, that special case of matrix multiplication. And okay, so once more, the Kronecker delta comes and helps. This is the I kth component. It's only 0 when I is equal to k. Summation collapses down again once more to Aij. But this time I look at it and I say, aha, well that is also the ith row of A and the jth component of that. And there you have it. EI transpose times A is equal to the ith row of A. So if I want to select the ith row of A, I can just left multiply it by a row, the standard basis ith row. If I want to select the jth column, I can just multiply on the right by the jth standard basis vector. Now, an immediate consequence of that is this one, right? So if I look at EI transpose A, EJ, what's that going to be? Well, that's going to be EI transpose times what? Times the jth column of A, right? But that's the ith row of the jth column of A, but hey, that's just Aij. So once you know this row and column thing, then it means that if we do this kind of sandwich multiplication by the ith row vector and the jth standard column vector, then we can pick off the ijth component. This is also true for rectangular matrices. I'm going to stick to the square case just so that it's easier to think through. Now, another thing I should mention is just, I'm going to kind of skip over to these guys, and then we'll do that one last. So, I wrote this out before, I'll just kind of walk through it again. So if I take the dot product of two vectors, I can rewrite it as a row column hero. This guy was supposed to appear in a previous video. I'm sorry, he was off the frame. I'll put him here now. So it was supposed to be a row column multiplication, which gives you a dot product, right? So like ei.ej is also like, it's only going to be 0. It's going to be 1 when the I and j match up, if you think about it. And so that's the Kronecker delta ij. So there you go. EI transpose times ej is Kronecker delta ij. That's this part of the theorem. Now the opposite way around is interesting. If I look at the just switch the order of them. Then I've got n by 1 times 1 by m, which is n by n. And if I look at the kth component of that, then I can say, well, that's the kth row and the lth column of this, right? But then using what we just already worked out, that's multiply by L on the right to select the lth column, multiply by EK transpose on the left to select the kth row, use associativity of matrix multiplication to look at these, in the proper order. So these two, right? These two give me that, right? And these two give me that. But lo and behold, remember how we defined the matrix unit Eij? Sorry, make sure it's in frame. We exactly have the kth component of Eij, but this is true for arbitrary kth, so therefore, there you have it. Ei times Ej transpose is Eij. So we can build the matrix, the square matrix units at least, from products of the standard basis. In the rectangular case, you can still do it, but then you have to work with standard bases of different size, which you can do. And then finally, this guy, Eij times Ekl, well, I can look at that now in view of this. I can look at that as, well, what is that? That's Ei Ej transpose times Ek times El transpose, right? And well, you see what this is. By this, that's just Kronecker delta, right? So I've got Ei, Kronecker delta Jk, El transpose. And so pull the Kronecker delta out, Ejk, Ei, El transpose. But hey, that's exactly the matrix unit, Eil. And by the way, it's an unfortunate term because a matrix unit's not an invertible matrix. It doesn't have a multiplicative inverse. We'll talk about that in the next lecture probably, or video. So there you have it, the Kronecker delta Jk Eil. And so these are neat formulas. You'll see in the next video how we can use these to study things like diagonal and triangular matrices and such. And they're just nice tools to have, this Eij and little ei. Anyway, I'll cut it off here. Thanks.